started now. Okay, so today we're going to be continuing with the topic of number theory and covering some different aspects to number theory that we haven't before. And today is session 4. So today is also the last session that I will be teaching. And following from now on, the next 2 weeks is going to be taught by Tim Wang, so he's also an instructor, and he'll be covering combinatorics and geometry. But anyways, we can keep going with our number theory. And okay, so today we'll be covering some content that includes like properties of natural numbers, like Fermat's little theorem, which some of you may already know about, and then Euler's phi function, and then Euler's theorem, also known as like Fermat Euler's theorem. But anyways, we can get started. So to start off with something that you guys may be more familiar with, like factorizing natural numbers. So last week we did talk briefly about like prime factorization of a number. Does everyone remember that? Can anyone remember what's special about like the prime factorization of different, like a number? We did mention one thing about it. Does anyone remember? Probably it's also on this, like the screen, but it's not exactly bolded out or made explicit. Yes. Okay. So really good answer I got is that each number has a unique prime factorization, right? So it has to be unique for different numbers. Okay, so now let's consider, with that in mind, let's consider the prime factorization of a natural number n, right? We can express it as, so p1, p2, p3, all the way until p, okay, it's not a very good use of variables. I'd say, let's say this is like capital N. Okay, so let's say we have a number, capital N, and then it can be expressed as, in terms of the primes, p1, p2, and then all the way to pm. So this little n is regardless of the number itself, right? It doesn't have to be equivalent. So that's why I said it's not a good use of variables, because if we use lowercase n and then lowercase n here, it suggests that it has the same number of prime factors as the number itself, which is probably very, very, like, not going to be true. Okay, so E1, E2, all the way until En are the exponents of these prime factors, right? So if this prime, like say this number is divisible by 4, right? Then it has a prime factor of 2, and the power has to be greater or equal to 2, right? So if it's divisible by 4, it has to have at least this within its prime factorization. So I'm sure you guys are pretty familiar with this. Like, as long as you get the concept that you can express it as primes, you're probably all good. And now we're just going to talk about further about some properties we can use prime factorization for, which can be actually really helpful. So now we can consider this total number of factors. So some questions they might ask you are find all like the total number of factors of some number, right? And not be like, you could count them up one by one. Sometimes that gets really hard, especially if the number's really big. So actually, like, the easier way to do this is to actually just consider the exponents of your prime factors, right? So we have our number here, and we know that these are the exponents, and it's actually the total number of factors is the exponents plus 1 and then times together. So, okay. Does everybody understand the definition of that? Yes? Okay. Good to hear. Right. So, like, how can we think about this intuitively? So it might not make sense if we just look at this formula by itself, but like, how can we actually think about it intuitively, right? So let's consider a factor of n, right? It has to have, well, it has to be divisible. So a factor, let's say a factor d. Right, so d divides into capital N, right? So it has to have like a common prime factor as it, or it has to like divide somehow into N, right? So we can express d as P2 or Pn, but sometimes it might not have all the prime factors. It doesn't necessarily have to have all the prime factors, the same prime factors as N. It just can't have any other ones. So if let's say it's to the power of f1, f2, fn, right? We can consider what the value of these exponents can be, right? It can be 0 because if this prime doesn't exist within our factor d, well then it's 0. It can be like anything below or equal to 1, right? So f1 has to be below or equal to 1, f2. We have this condition, right? Because as long as it satisfies this condition, it can divide into n. Like we talked about a little bit, the greatest common divisor last week, not like on Tuesday, it has to fit into n, right? So it has to have an exponent of each prime that is smaller than the exponent of actual n. Does this make sense to everyone? Yes. Let me know if you guys have any questions. And we can go over it together. I'm saying that it can't be bigger than like E1, E2, or En, because if it were, it wouldn't divide exactly into n, right? Because if it were, then it would leave, say it had like, if f1 was like equal to E1 plus 1, then it means that d can't divide into n. Right, because it can't divide into any other prime factors like of n, but it's got a bigger exponent than n does, then it just won't divide. And you can try this out for yourself to see if it works. Now I'm saying this because with these conditions, how many values can we choose for f1? What are the possible values we can choose for f1? Well, we can choose which ones? Keeping in mind that d is a factor of n, or capital N. You guys have any ideas towards what values of f1 we can actually take? I mean, it should be pretty obvious if we just look at this, right? Okay. We can pick any value up to E1, right? So if say like you can pick these values, right? And how many are there of these? Well, it's E plus 1, right? So here's E1 values, and then we also account for 0. So there's E1 plus 1 values. Let's say possible values. For f1. And we kind of use the same idea for f2 and all the way to fn. And because they have these so f1 has e plus 1, f2 has e2 plus 1, and then fn has n plus 1. So then the product of all of these, we notice, is actually just the total number of factors, right? Because we just pick one exponent from each of the possibilities, and there's e1 for this, e1 plus 1 for this, e2 plus 1 for this, and then en plus 1 for this, all the way down. So that's how you can think about about where we get this this formula from, but if you wanted to prove it a bit more like rigorously, you can think about it in a bit more depth if you have like free time or anything. Okay, so now let's look at the total sum of all factors, right? Okay, so this is a really good question, right? So why is it multiplied and not added? So we see that here we have the relationship that they're multiplied together but not added. So this might tie a little bit into like counting and combinatorics, which I'm sure you guys will go over a little bit later. But these things are like, say I have two options for one, so like 0 and 1 or something, and let's only consider if it was E1 and E2. And three options for what are the possible values we can have for this? Yeah. Let's use a variable f. It really matters. So what possible values can we get for that? Well, we can have p1 to the power of 0, p2 to the power, okay, so that's 1, 2. So f2 can either be 0, 1, or 2, and f1 can be 0, 1, right? So we have this. Right, how many options is that? So that's 1, 2, 3, 4, 5, 6. So instead of like if we added them together, we'd get something like 5. But if we multiplied them together, we'd get 6, right? It's because we want to pick one from this. So there's two options and we pick one of them, right? And then for this one, there's three options and we want to pick one of them. So it's two options here and then three options here. And it's like a multiplicative relationship because they're independent of each other, right? Because we have to choose like both of them. So we first have to choose F1 and then we have to choose F2. And we can choose any possible value within it. So it's multiplied together. Does that answer your question? Okay, yeah. We can keep going. Okay, so now let's look at the sum of all the factors. So sort of like a similar sense, we want to account for all the possible factors, like exponents that are smaller or equal to E1 for our divide, like in our factor, right? So we can either have P1 to the power 1, P1 to the power of 2, all the way on to P1 to the power of E1, right? So it's the sum of all of these times the sum of all of these and the sum of all of these. So it's all the prime factors added to the highest power, and then you times them together. If you would like to, you can definitely prove this. We won't go in too much detail on that today, but if you do have any ideas, feel free to share them. But this is the general formula that will give you the total sum of all the factors, and this includes 1 and n itself, right? So it's all the factors, 1, and then all the way up to and including n. Okay, does everyone understand these two formulas? And if you actually wanted to like, not that I suggest any of you guys should, if you wanted to like expand the brackets for the sum of all the factors, you'll find that, well, every one of your variable, like every result you get when you add them together is going to be every factor you can possibly have for n. If that makes sense, we can move on. These two are really useful when you are trying to do like calculation problems. So what we can actually do is let's try a like really quick example just to give you guys a feel of how you might use these. It's fine. Okay, I'm just gonna pick a random number. I don't really know. Okay, it didn't work by. And you guys have like um, okay, so let's say we give you guys 2 minutes to have a think about this and try it for yourself. Just a reminder that these are the formulas that we're looking at. So first and foremost, I'd start with finding the prime factorization of our number, right? And if anyone has like figured it out, feel free to share your answer with everyone. Okay. Jesse, did you want to share how you got your answer?
I did a prime factorization and there is 5, 3, 23, and I used the formula is 2 times 2 times 2 equals 8.
Yep, that's really good. So, yep, that's how you'd get the total number of factors. Yep. And for the second part, I don't necessarily want a number, like, because the number's pretty big, so it might be a little bit confusing if you were to, like, calculate it. But how would you guys, like, think to do it? Anyone want to share their ideas? You would just put it into the formula, so does anyone want to share? Yep. Okay, really good. So, yes, exactly. So I've seen a lot of good answers, and it should be 1 plus 5, and then that's 20, right? Yeah, really good. And if we really wanted to, I guess we could extend this, right? So, and it should be like, and if we look here, that's 1, 2, 3, 4, 5, 6, 7, 8. So each of these is a factor of our 3, 4, 5. So we can see quite clearly how factors, because if we expanded it out and we didn't like add yet, we don't add them together yet, just gives us all the factors of our number. So that's how you can think about it. Okay. Yeah, that's good. An idea of this sort of idea. Okay, then we can move on. So let's move on to the next one. So a little bit of a recap from last week, which is mainly the idea of like modular, which is really, really important, especially also in today's session. So just remember that for arithmetic modular, like addition, subtraction, and multiplication is all the same. just have to be a little bit more careful in division. And well, today we'll be mainly talking about like exponential stuff. And I guess you can think about it in terms of multiplication, right? So if A is congruent to B mod M, then if I do like A times A times A times A, E number, like E times, it should be like the same as B times B times B. Right. So that's the sort of idea. You can just think about it as like multiplication. Does anyone have any questions from last week that last session that you may not have really understood or you wanted to clarify? Okay, so when do we usually use like modular system? Well, first we're going to come across it like really soon, but also it's actually very useful in a lot of problems when it's asking us about like divisibility. So if it asks like, oh, prove that this something 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 is divisible, maybe like an algebraic expression like x something. I can't think of one off the top of my head, but like something like this, and it asks, when x is an integer, prove that this is always divisible by like 3 or 5 or something like that. You can actually prove it using like modular things, and it's just a very much simplified version of considering remainders, because it can be like really confusing sometimes when you have to express everything like x equals n plus r or something. That's a lot of variables, right? But when you are in modulo, you can really just simplify it down to something like this, which is actually a lot easier if you think about it. Yeah. Okay, so there's a lot of uses, especially in number theory. We come across a lot, and today I'll be looking at some of those things. Okay, so let's look at some exponential in the mod system. So can anyone tell me, like, just really fast, we'll run through the answers for these, right? So what is 3 to the power of 1 in mod 7? This should just be really quick. Yeah. Okay, so this is 3. What about the next one? 3 to the power of 2? 2, yep, okay. 3 to the power of 3. Yep, 6. What about 3 to the power of 4? Yep, 4. What about 3 to the power of 5? Yep. Okay. And what about next one? Yep. What about the next one? Yeah, okay. And I will give you guys a tip. So like, when I have these numbers, I'm not like, I'm sure most of you guys aren't actually calculating, oh, what is 3 to the power of 5, 3 to the power of 6? Because like, when you get to really big numbers, you can't do that by your head, right? But we can look at like the relationship between these numbers, right? It's times 3. And remember how we talked about like arithmetic modulo in terms of like multiplication? Well, if this is this is congruent to 5 mod 7, well then we just times this 5 by 3, and that's 15. And 15 is 1 mod 7, right? So we get our next answer. So you can kind of, instead of actually timesing it out on this side, times it down by 3 this side. And it makes your life a lot easier, just because you can just times by 3 and you don't have to actually find the value of 3 to the power 6 or something like that. So keeping that in mind, what do we have for 3 to the power 8? Okay, yep, 2. Yes, and this is like sorry, their equivalent. Nine. That's what is. Yep, 6. Really good. What about the other one? Next one. Yep, 4. Next one. 5. Yep. Oh, last one. Yep, 1. So what do we notice? We notice that it's almost like after 3 to the power of 6, it's like cycled back, right? Because we have the same, these are all the same ones, right? And it almost suggests that, oh, is there like a sort of pattern going on? Does it always cycle back to like 3 to congruent to mod 3? Congruent to 3 mod 7, sorry. Like, but how can we actually like explain this pattern, right? So it looks like there is a pattern, but how do we explain it? Well, we can sort of look at this first theorem, which is very, very useful, and it's called Fermat's little theorem. So a lot of the times when you have like a number to a really high exponential, just by like actually finding the number and then dividing it, right? Because that's really, really hard. So there are a lot of theorems that you can use to help simplify this a lot. And it kind of accounts for any patterns you might see going down the list like we did before. So there's a pattern, and we can explain this pattern using Fermat's little theorem. So what does it say? So first, we have to think A is, it says integer, but I guess we can think about it as a natural number. So natural number is like greater or equal to 0, integer that's greater or equal to 0, right? Let's actually just say it's just a positive integer. And P is a prime number, right? So P has to be prime. And one other condition is that the greatest common divisor has to be 1. So they have to be congruent. So no common factors except 1, and P is a prime, and A is a natural number. So what Fermat's little theorem states is that A to the power of P is constant. Right. So if we think about this a little bit in context, like using the example we had before, well, it kind of explains this, right? So we're in mod 7, P equals 7, and 7 is a prime. Mod, A is definitely co-prime with, like, so 3 is definitely co-prime with 7, so it's okay. We can use A equals 3. So A equals 3. Then we have 3 to the power of, so 7 is congruent to 3 mod 7. Is this true? Well, we can have a look for, right? And yes, it is true, because we can see something like this, right? Yes, so at least for our first example, it is definitely true because it satisfies what we were looking at before. So this is tick. Okay. So now sometimes A to the power of P is congruent to A mod P isn't always the most useful. But what we can do is, because we know that A and P are co-prime, we can divide both sides by A, right? Like we talked about last week, we are allowed to divide in this case, and if we do divide, we get something like this, which is actually very, very useful. Because what is special about 1? If we're thinking about like exponentials. Any ideas? It's not a like trick question, or it's not very hard, it's just whatever comes to your mind. Yes, so 1 to whatever power, like it doesn't matter how high the power is, it can be a huge number, it's always going to be equal to 1, right? And this equal sign. And this is a very useful part, because now if we wanted to know what is A P to the power of 1 2 congruent to mod P, what would that be? What would this part be? So notice that this is to the power, so it's like, so first we know a p minus 1 is congruent to 1 mod p. So what is the difference? Yeah, so if we actually squared all of this, it's still going to be equal to 1. And it doesn't matter if we squared it, cubed it, or like a higher power, it could be to the power of n, like any power that's an actual number, it's still going to be congruent to 1. And we can get the conclusion that n, because when it's exponents, right, we times, so we get something like this. Right, and this is really useful because we now know like a pattern that every number that can be like expressed in sort of this form or has a factor of p minus 1 is going to be congruent to 1 mod p. Right, so that's really useful. Okay, then, with that in mind, like what we talked about, let's try the first problem. Let's try this problem. And like usual, we have around 2 minutes to think about it. And if you do have any ideas, feel free to share. Right, any ideas? No? Okay, that's okay. We can just start and yeah, okay. So now we know these two conditions, right? So using fermat's theorem, we know these two conditions. And it can help simplify our problem down, right? Because it's to the power of 103. And we're not gonna actually figure out the value of 7 to the power of 103. Okay. Okay. Let us first go on. Let's consider what 103 divided by 17 is. Like what? Okay. Let's write in this one. So we're to write it in the more. So a really good response, and it is 1, right? So maybe you can possibly use this. Or we can consider 103 60, right? Because if we wanted to use this condition, would consider this. If we want to use this condition, would probably consider this, right? So what is 103 congruent to in mod 60? Okay, it is 7. Okay, cool. So we can write right, so we either express it like this or this. I'm not too sure which one's gonna be more useful, like either. But okay, I think both will give the same answer, right? So if we were to use the first one, then we're trying to find the value of this, right? And then times, right? And does this make sense to everyone? So if we expressed it as like this or this, both work. Okay, cool. And after we've done this, we can now simplify it, right? And hopefully it makes things easier. I'm not too sure either. So let's say we try the first one. We have this. Well, we know that 7 to the power of 17 is congruent to 7 mod 17. So we could substitute that in. Then we should just get 7 to the power of 6 times 7, right? This congruent, so 7 to the 103 should be congruent to this. Or if we use the second one, let's try the second one as well. If we use this, we would get 716. Right, and this is also 7 to the power of 7 mod. Okay, so I think that's as far as we can simplify it. I think leave it here because the rest might not really have anything to do with like Fermat little theorem, especially. But at least we've simplified it, right? So we've simplified something like finding the value of 7 to the power of 7 is going to be hard as well, but it's going to be easier than finding the value of 7 to the power of 103, right? So this is what like Fermat's little theorem can do to help us out. If we did want to simplify it a little bit further, we might find the value of like we could do something like this and substitute it like to 7 to the power of 7 is equal to 7 times 7, right? So maybe we wanted to substitute this. This doesn't have too much to do with polynomial theorems, so we won't go into too much detail. But if you did want to actually find it, like the value of the remainder, such that it's between 0 and 16, you could keep going and keep simplifying like this, and you'd get your answer. Okay, does everyone understand how we used polynomial theorem in this question? Yes, no. Okay, so I've heard from someone that it might be 12. I don't know. I have to take your word for it. Okay. So, don't really understand. Let me know which part in particular you might be a little bit stuck with, and we can definitely go over it a little bit more in detail. So, great. Personally, I like to use, I think, the second one because I find dealing with 1 is a lot easier than dealing with like 7 or like some other number. So if we were just to look at the second example, what we can do is we know this is true. Then we can actually rewrite 7 to the power of 103 as this, right? This might require a little bit of knowledge, like with exponentials. So if we have something like p to the power of ab, we can definitely write it as p to the power of a to the power of b, right? So this is a little bit like outside knowledge in terms of algebra and stuff like that, but we can write it like that, and that's what we're doing here. So we've written 7 to the power of 16 times 6 times like this, like again, and we've written it because it makes substituting a lot easier, right? So now we can use our second equation that we know from Fermat's little theorem that 7 to the power of 16 is congruent to 1. We can substitute that in, right? And we get something like 103 is congruent to 1 to the power of 6 times 7 to the power of 7, right? Does this clarify things, or if that's not the part that's not too sure about, let me know, and we can go over it in a little bit more detail. Because if you guys do have any parts that you're uncertain about, there are probably other people who are also uncertain about that part. So definitely let me know and we can go over it in a bit more detail. Because this is a really useful theorem, so it would be really good to get it down and know how to use it and know when to use it. Does everyone understand? Okay. Okay, of course. So, Fermat's little theorem, let's reiterate it again. What are the conditions? Well, it basically states that if a is some integer, a natural number, so that's an integer greater than 0, and p is a prime, right? So p has to be a prime, and the greatest common divisor of a and p must be 1. Then we can come to the Fermat's little theorem just tells us that a to the power of p is congruent to a mod p. So when we divide a to the power of p by p, we get a remainder of a. So, or another way of thinking about this could be that Fermat's little theorem tells us that a to the power of p minus a is divisible by p, right? So that's another way of interpreting it. So this is what Fermat's little theorem tells us. And yes, if we wanted to use it, if we wanted to use this part, so this condition, we just divide both sides by a, right? And if you recall from last week's, last session, we can divide both sides by a because a and p are coprime. So that's possible. So that's something we can definitely do. So for the second exercise, I think we can leave it as for anyone that's interested and want to give themselves a bit of a challenge, because it is definitely a bit harder. So now we can move on from Fermat's little theorem if everyone is happy. Okay. Let's move on to Euler's torsion function. Okay. It's very confusing when you first learn about it, and it's kind of you don't think it's very useful because sometimes you don't know where to use it and stuff like that. But okay, so Euler's torsion function is either written sometimes like this or this, right? So they both stand for the same thing, and they're both they look similar as well, so it shouldn't be too hard to memorize. But okay, so the name suggests, it is a function. So if you remember from our algebra class, what properties do functions have? So there's one, or I guess two specific things that define a function. Can anybody remember what those things are? Yes. Okay. So it requires an input and then it requires an output, right? So that's what a function is. So there's an input and then there's an output. So for Euler's totient function, the input domain, like we talked about in our algebra class, if you weren't here, it's okay. Just sort of like input is what you put into the function and output is just what you get, right? So an input domain is the numbers that you're allowed, or the values you're allowed to put in the function. So you're allowed to put natural numbers into the Euler's totient function, or like the phi function. And the output you can possibly get is also going to be a natural number. So yeah, so those are like how Euler's totient function is defined. So what does the function actually represent? Well, it represents the number of natural numbers less or equal to our input n that are relatively prime to n. So that might not make too much sense by itself, but we can think about an example of what if our input was 6, right? So when we have our input, we need to consider all the numbers that are co-prime to 6 that are smaller or equal to 6, right? So all the numbers below or equal to 6 are 1, 2, 3, 4, 5, 6, right? So which ones were actually co-prime to 6? Well, co-prime is defined as like GCD of 6 and the number of, say, k is equal to 1, right? So 1 and 6 obviously have a GCD of 1, and 5 also satisfies the condition, right? Because 2 and 6 have a common factor of 2, 6 and 3 have a common factor of 3, and then 4 and 6 have a common factor of 2, 6 and 6 have a common factor of 6. So only 1 and 5 satisfy like being co-prime, right? So 1 and 5 are co-prime. Okay, now with that in mind, how many numbers are co-prime to 6? So how many are they? Yes, exactly, right? So there's 2. So there's 1 and 5. 2, yeah. So then the value of the phi function, or whatever you want to call it, is going to be equal to 2. Right? So that's how we get it. So that's how we define the function. Does that make sense to everyone? So you need to consider the number of natural numbers less or equal to our input that are co-prime to our inputs. Yeah, that's how we can think about it. So if you also wanted to trial it out a little bit further, you can consider what if our input was 30, right? That's a bigger number, so you have to consider more of them. So now let's think about some properties of the phi function. So, okay, so what if our input only has one prime factor? So it's p to the power of k, right? Then what are the total numbers that are co-prime to it? Well, first we have to think how many numbers are actually smaller or equal to pk. So there are 1, 2, 3. We need to consider all these numbers, right? And in total, there's pk of them, right? And now we can think of the numbers that are co-prime to our input as the total number, like our input minus all the numbers that aren't co-prime to them, right? So if they have we can just subtract all the factors away and we can get our value, right? So what are the number of, then we have to consider, we can refer back to what we had before, and we can consider, well, what are the total number of factors that it actually has? So that's gonna be pk. So p has the common factors of p, and we ignore 1 just because like it is co-prime even though it is a factor. So right, and there's also 2p, right? 2p squared, 2p3, all the way until like 2pk minus 1. And if we count up all the factors, all the numbers that have a factor of p, or isn't co-prime to like p of k, there's actually pk minus 1, right? So we can think about it as pk divided by p. So every p numbers, so 1, 2, 3, p plus 1, p plus 2, 2p. So every p numbers, there's a factor of p. So that's why we divide by p. So we want to remove all these numbers. So in total, there should be pk divided by p. So it accounts for both of these parts. And if we factorize it a little bit, we get something like this. Does this make sense to everyone? Yep. Okay, good to hear. Cool. Okay, so that's how we get the phi function of p to the power of k is equal to pk minus 1, p minus 1. So that's something like that. And then we can consider, okay, what if we have two primes, right? So p1 to the power of k1 and p2 to the power of k2. We can write it as, actually, as long as these two are co-prime, we can write it as something like this. Right, so we can split it. So that's what the second property is sort of talking about. And it's talking about something like this. So if m and n are co-prime, we can write the phi function of mn as phi m times phi n. Okay, does that make sense to everyone? Yeah. Okay. Let me know if you guys are a little bit like unsure about anything and we can go over it. Yes, no. Okay, we can move on. Sure, we can move on, I guess. Okay, then what if we just have a general number n, right? Okay. Yes, I will definitely send these slides to you guys a little bit later. So now let's consider a general number n. So first we have to find the prime factorization of n, which in this case is nkr, right? So that's the prime factorization of n. Well, from before, the phi of n, we should be able to split every prime out, right? So we can split every prime out so that it's the phi of p1, k1, p2, k2, because all these numbers are co-prime. And we get something like, okay, PRKR, right? And if we do this, like we see over here, we can then use our first property that we write it as okay, so then we can write it as something like this, right? So we just find them each individually. And what we can do again is if we take P1 out from here, so we factorize a P out from here and we add it to this side, we can write it as this, right? And it looks sort of funny because this forms like a fraction and it's not an integer anymore, but we can do that. Let's just we can do that. And if we do something like that, we get this times all of this, right? And we notice that this is the prime factorization of n. So our motivation of actually dividing out P1 and P2 from these bits is to actually form n again. So we form n over here, and then we have some part, like this part, which seems really weird because it's like a fraction and it's not even integers. But if we do that, we can get n. So that's sort of how you can understand it. And this is really useful when we simplify like this because it's a lot easier. Now, as long as I know the prime factors of my number n, I can find phi n. I don't even really care about necessarily the exponent values. So I've simplified it down so that I only need to know the primes and my number n. Does that make sense to everyone? So this is definitely like one of the more confusing parts. So like when I first saw this as well, I was like, why do we even need to know this? Like, what are the uses of this? But it turns out it's really important and it can be useful in a lot of cases. So does everybody understand this part that we're coming from? Yeah. Let me know if there are some parts you might not like understand entirely or you'd like to go over a little bit more. Okay, then let's move on and try to, what we can do is let's first do an example or problem. So what is the phi function of 3, 4, 5? And for anyone who's super speedy, I'll pick another number. I don't really know, but sure. So let's try finding this before I recall it being, what was it? Was it this? I think. Okay. And then we can just substitute it in to what we had. So first it's 3, 4, 5 times 2 to the power of 3 times 4, because if we just substitute it into these parts, right? So it should be something like this, right? And what we notice is that, well, these, because they're each of these is to the power of 1, so it actually cancels out perfectly. So 3 times, this should really just be over 3, 4, 5. Yep. So what's a prime factorization of 6 to 1? Any ideas? So what's a prime factorization of 6 to 1? Okay. Okay, so it's definitely divisible by 3. And 6 to 1, let's divide by 3, 2, oh, 7. We can divide by, I'm pretty sure we can divide by 9 this time. And 2, yeah, we could divide by 9. Okay, anyways, yeah. So it should be something like this. Is this what everyone got? Yes, fabulous. Okay. So if we substitute this into the equation, we get something like 621 times 1 minus. Right, so if we can cancel this out, so we should be left with this. Is this what everyone got? We don't have to find the actual value of it. Yes, no. Right, so I think I actually missed Euler's theorem. So Euler's theorem states that states this. Right. So yeah. It follows on directly from the phi function because we need to use it in the exponent. And it works in very much the same way as we would consider Fermat's little theorem. And it goes like, it just tells us that whenever it's something like this as well, we can consider this to the power of like b, it's always mod congruent to 1 mod n. Yep, so does everyone understand the definition of that? And remember that the GCD of A and N has to be 1 as well, or else it can't be coprime, right? Okay, so like notice that this is very similar to Fermat's little theorem because it's like same, we're looking at exponents, and we have the same condition that A and N have to be coprime, except this time N doesn't necessarily have to be a prime. Right, so also remember that the phi function of P is just going to be minus 1, right? So if we consider Fermat's little theorem as a special case of, okay, so GCD is greatest common divisor, so it's the largest number that is both the divisor of A and divisor of N. Yeah, so we refer to it like as GCD, like basically everywhere. And so, yeah, so just remember this, so we can just say this. So this is a special condition of the Euler's theorem. So this is really useful because now we don't really care about the value of n that much as we would for Fermat's theorem, that it has to be prime, right? So this is really useful. And okay, so we have this. First, so this is a really long chain of values, right? So this by itself doesn't look like it has anything to do with Euler's theorem or Fermat's little theorem at all because the numbers are really bad and it's like addition, which is something we're not familiar with. But if you are a bit more familiar, either with like geometric sum or anything like that, or just in general, you might see it a lot. We can actually express it like this, right? Because if you consider this as a geometric sequence, well, then it's sort of like it's timesing 2 every time. So if we want to add something like this up, we would just use this. Right, so does everyone know the sort of saying or the condition that this is true? Yes, no. But it is, if I added 1 to this side, right? If I add 1 to this becomes 2, right? So I can cross this out and add 2 here. And then 2 plus 2 is actually 2 to the power of 2, right? So there's a missing 2 to the power of 2 here. So it kind of like, it pushes things over and then it causes everything to increase until we get something like this. So we get to, yep, so our left-hand side plus 1 equals, so obviously our left-hand side is equal to this, right? So if you're not too familiar with it, don't worry. But well, this is just true, and we can use this, right? And this looks a lot better than what we had before. So let's consider what the phi of 1, 2, 5 is. So remember that 1, 2, 5 is 5 to the power of 3. So what would phi of 1, 2, 5 be? Any ideas? Okay, so how would we get it? We could do this, and then we just do this, right? If we substitute it into our equation or something, we get this. So indeed it is 100. So yep, we know phi of 1, 2, 5 should be equal to 100. So what does this mean? Well, if we use Euler's theorem, first we see that GCD of 2 and 1, 2, 5 is equal to 1, so we can use it. And then we would do something like, and because we know phi of 1, 2, 5 is equal to 100, so we have this condition, right? So 1, 2, 5. And this is really useful, right? So let's multiply, because we notice here that our one is 2 to the power of 2 to the power of 101. So what we can actually do is we just do this, right? So we times both sides by 2, and we get this. So if we subtract 1 from both sides, we should get something like this. So our answer should just be 1. It should be congruent to 1. So 1 plus 2 plus is congruent to 1 mod 1, 2, 5. Is everybody following? Yes? Okay, great. If anyone is also interested, I guess just for geometric series, like it's when there's a common like difference, right? There's a multiplicative difference, so something like this or something. Or if we're finding the sum, can anybody remember the formula? Yeah. Okay. Okay, so the sum should be something like this, right? Does this ring a bell for anyone? And yes, I'll send the this entire PowerPoint to you guys after class. So with all the writing that we have, and yes, you'll be able to refer to that if you'd like. But other than that, I think that ends us for today. And today is going to be my last session teaching in this course. But if you guys have any questions in the future, just email me or anything. And